All right, good morning, everyone. Hope you all had a great break. And yeah, I had a good break too. The assignment is due tomorrow. It's normally due Tuesdays, but remember I extended it just 2 days. So that next assignment is going to be due tomorrow, the normal time. I am planning to get back on track with those on Tuesdays. So I'm going to be releasing the next assignment today sometime. But what you'll notice about that one, I'm planning for it to be a bit shorter since you only kind of have Thursday to Tuesday. Plus, we also didn't have class Monday, so there's kind of less material to cover anyway. So I think that is going to work out pretty good. So we'll have a short one. We'll make it due next Tuesday at the normal time, and we should be back on track there. The quizzes I can comment on. The quizzes are all completed, and I checked out the grades, and I think you can see your grades if you just go back in. I think it shows you your score on the midterm. I think it, or no, it's not a midterm, it's just a quiz. I think it will show it to you if you, like once the deadline hit. So I think the way I set that. The class average for that was, I think, 79, which is pretty good. Not really concerned for most of you there. If you didn't do as well as you'd hoped, then, I mean, it's maybe a check to kind of let you know where you're at so far. And certainly there's time to improve and, you know, get it on track for the next one. Remember our marking scheme too, how you can kind of take 5 points off of any one assessment. This assessment, I think, is only worth 5 points towards your final grade. So if you pick this one, well, you don't have to pick. I'll pick for you based on what's in your best interest. If this is the one that gets dropped, then that means that last quiz was actually worth 0. And so if you think of it that perspective, great if you did well. That's fantastic. That's 5 points you don't have to worry about now on your final grade. But if you weren't happy with your grade, if you thought you could have done better or will do better, this one can kind of get erased, if you know what I mean. Okay, so what we're talking about in the next lecture today is going to be this relationship between thermodynamics and equilibrium. And they're sort of fundamentally linked, fundamentally related to each other. And we finished our last class talking about this particular reaction or this particular equation, which relates the standard Gibbs energy change, the delta G zero, with the equilibrium constant, K. So this is, and I think I might have said this last class, this is one of the most fundamentally important equations in all of science, and not just chemistry. It's a very, very important one because it tells you when you have a chemical system, you know, using the free energy change, the standard free energy change, you can tell exactly what the position of that reaction is going to be when it hits equilibrium. And so we're going to talk a little bit about this today, and we're going to watch how this equation can play out, how we can apply this equation to a real world situation. What I want to do first, though, is really talk about what this delta G zero means and how it's different from delta G without that zero that's up there. Slides aren't up. Really? You can't see my slides. I guess you can't see my slides. Thank you. There, now slides should be up. Thanks, Adrian. Yeah, so what we want to do is talk about the difference between delta G zero and delta G, and they are different things. It's easy to look at that little zero there and ignore it and think, well, we're talking about delta G. It's just a single thing. It's like, no, there's distinct meaning behind that delta G zero versus a delta G. So I'm going to show you what delta G zero means. Delta G zero means it's the delta G of a reaction when everything is in their standard states. So So what does standard states mean? Well, it means, first of all, generally speaking, it means the temperature is 298. If it's a solute, so if it's something that's dissolved in water, like an acid-base kind of species, it means all the concentrations of everything that's in there is 1.000 molar. Okay, so the delta G zero will tell you what the delta G is for that reaction when everything, products and reactants, are all at 1 molar. If it's a gas, all the gases will be at the same pressure, which is 1 bar. Okay, 1 with infinite zeros behind it. So when we look at this delta G zero, many times when you're looking at a chemical reaction, everything isn't at 1 molar. Like if you start a reaction, probably you have high concentrations of reactants and low concentrations of products. That would not be a standard state, and the delta G zero that you would have for that reaction could not be applied in that particular situation. So what's an example? Like let's say you have an acid-base equilibrium where you have HF plus water is in equilibrium with H3O plus. Remember, this is AQ. This is a liquid. This is AQ plus F minus AQ, aqueous. So if you created this situation where everything here was 1 molar, water is a pure liquid. So the other thing I guess here is pure solid or liquid is whatever the standard state of that substance is, which for water is a liquid. Don't worry about that one. 1 molar, 1 molar. The delta G zero would then tell you what the driving force is for this particular reaction in that state where everything is 1 molar. So what that means is if delta G was negative, delta G zero was negative, then this reaction would have a driving force to proceed forward, to produce more products. If delta G here was positive, it means the reverse reaction would be spontaneous, and some of those products, those 1 molar, would move backwards. If you think about a reaction, a normal type of reaction, where let's say we have HA plus water, again, we have an equilibrium where we have H3O plus A minus. Normally what you would do is start with all reactants and then see what happens. If you had all reactants, let's say you had 2 molar, and well, this is the liquid, and you started with 0, 0, the delta G here is not going to be the delta G zero. The driving force for this can only push to the right. It can only go in that direction because you can't go left because there's no products to create more reactants. So the delta G here must be negative in this particular situation. But the delta G zero can be positive or negative, because the delta G zero is the number if everything was 1 molar. So this delta G zero, then you can kind of think of it as like, you know, it's only under one particular situation where that number can apply, but it's an important reference point that it allows us to define delta G's at any other set of conditions that aren't those specific conditions where everything is 1 molar, or in gases everything is 1 bar. So hopefully this is sort of clear. The delta G with no zero is sort of like the actual driving force to go forwards or backwards for that system under whatever conditions that system is under. Whatever temperature, whatever concentrations or pressures, delta G will tell you whether you're forwards or backwards. Delta G zero is just this reference point that tells you whether the reaction will go forwards or backwards if you start everything off at 1 molar or 1 bar. Another example is if you look at delta G zero equals minus RT natural log of K, and you think of a reaction where delta G equals is delta G equals 0. Okay, this would mean that if delta G equals 0, K equals 1, according to this equation. Because ln K, ln of 1 is 0, so that means delta G would be equal to 0. That would be a situation where there's no driving force to go forwards or backwards, so this particular system would have everything at 1 molar, and it wouldn't move. There'd be no driving force to go forward, no driving force to go backward. In fact, it would already be at equilibrium. So that's what delta G 0 would mean in that case. Here's another example. So let's say, here's another way of viewing the same thing. Let's say you have starting materials, and let's say over here you have products. Okay. And you can have a reaction that, let's see. You can imagine if you started out with 2 molar starting material, and if you go to 100% conversion, you go to 2 molar product. What I'm going to show you here is delta G would be a situation like this, where at this center point, we could say both starting material and product equals 1.00 molar. Okay, so under this set of conditions here, this would be standard conditions. Everything's 1 molar, so we could say this would represent delta G 0. If you happen to be over here in this reaction, then that's just a delta G. There'll be a delta G here, and the delta G would be negative, meaning it's downhill to move forwards. That means there's a driving force to go here. Once you're at the bottom of this well, that delta G equals 0, and if that works out with everything at 1 molar, then we would say the delta G and delta G 0 are the same thing. This would be a situation where K equals 1, equal amounts of products and starting materials at equilibrium. Hopefully that helped just a little bit, because we are discussing delta G and delta G 0 quite a bit together, and there is a subtle difference there, right? Delta G 0, everything's at 1 molar, delta G, not the case. Okay, so here's a situation like the one I just showed you, where you could have either pure starting material or pure product, and when you start this reaction off, if you just start with pure starting materials, you're going to move towards products until you reach equilibrium. When you've reached the minimum here, delta G equals 0. Okay, so that delta G equals 0 just means there's no driving force to go forward, no driving force to go backwards. You're at the minimum here, but delta G 0 is not the same as that delta G, right? Delta G 0 is assuming all the products and starting materials were 1 molar, would you go to the forwards or go backwards? So this one you can kind of see the minimum here, right? The equilibrium point, the point where you're at the minimum delta G, minimum Gibbs energy, is close to the right, meaning you're going to have a lot more products when you reach that minimum than you have starting materials. So this would represent a reaction with a delta G that's negative. Negative delta G's favor products, and you can actually work out the equilibrium constant here using delta G 0 equals minus RT ln K. So in other words, this delta G 0 is another measure of the equilibrium constant. A large negative delta G means a large value of K, which means at equilibrium is going to favor products. A positive value of delta G means it's going to favor reactants, like you would have in this case. You see delta G is a positive number. When it's positive, that translates to a small value of K, somewhere between 0 and 1. And that means that when it reaches equilibrium, when delta G is 0, then you're going to be favoring reactants rather than products. This is the situation I looked at before, where K is equal to exactly 1 and delta G0 equals 0. What that means is if you have pure starting materials and pure products, those have the exact same Gibbs energy. So the delta G going from 100% A to 100% B is 0. Okay, problem time. Let's apply some of this. This gets very tricky and very muddy, and the difference between some of these thermodynamic constants is sometimes hard to keep straight. I know that's definitely the case for me, and part of it is because I find these values they're conventions, right? There's nothing special about 1 molar or 1 bar pressure. It's just somebody decided they needed a reference concentration and pressure, so they picked that. There's nothing fundamental about those particular concentrations. And because a lot of these conventions are just chosen by people at certain times, like 25 degrees, there's nothing special about 25 degrees. Apparently it's room temperature, but I don't know, I find that too hot for room temperature, like 21 degrees. Anyway, we have this reaction where we have carbon monoxide gas reacting with 2 moles of hydrogen gas in equilibrium with methanol, CH3OH gas. In fact, this is a very important reaction industrially. It's called the steam reformation reaction. Generally, you start with methanol and you want, actually, I think steam reformation starts with methane, not methanol. But in this reaction, you want it typically to produce the hydrogen gas you have on the left, because hydrogen is useful in all sorts of things, like hydrogenation for fats, for butter, you know, fake margarine and stuff like that. We want to calculate K, and to do this, what we need to do is use the equation delta G0 equals minus RT ln K. So if we want K, we need to get delta G0 first. We know how to do this using delta G's of formation. We have the delta G of formation of carbon monoxide here. Hydrogen is a pure element in its standard state, so its delta G of formation is 0. So is its delta H of formation, but its entropy, standard molar entropy, is not 0. In fact, it would be very high because it's a gas. And then methanol's there. So we could say that the delta G for the reaction then is going to be equal to the sum of the delta G's of formation of the products minus the sum of the delta G of formation of the reactants. So the products are methanol gas, which you see on the bottom, minus 162.0 kilojoules per mole, minus the reactants, which is carbon monoxide, is minus 137.2 kilojoules per mole. And let me just get my trusty answer sheet. Negative 24.8 kilojoules per mole. So in this example, that's our delta G for reaction. That's a negative number. So what that means is if you start this reaction off with everything at 1 molar, I guess these are all gases, so it would be 1 bar. You put them all in there, same pressure. Under those conditions, which is delta G0, you have a negative delta G, which means this reaction would shift to the right. And when it came to equilibrium, you might have, I don't know, 1.8 bar of methanol, 0.2 bars, actually 0.2 bars of carbon monoxide, and hydrogen would be, that doesn't work out because of the stoichiometry, but you know what I mean here. This is going to shift to the right because we have a negative delta G when everything's at 1 bar. We need to convert this to the K. The K will tell us the exact position of this equilibrium. Okay, so to get K, we would say that delta G0 equals minus RT ln K. We could say that ln K equals minus delta G0 over RT, or that K equals E to the minus delta G0 over RT. So we can calculate that out. K equals E to the minus 24800 joules per mole. I'm going to convert everything here to joules so that we have everything in the same unit. R is 8.314 joules per K mole times the temperature, which is 298 K. And when you do that, you get K equals 2.2 times 10 to the 4. Notice all the units here go, joules go, moles go, Ks go, and you're left with a number with no units, which is what you want when you're dealing with equilibrium, because equilibrium constants, by definition, do not have units. That K value is a pretty large number, 22,000, suggesting that this equilibrium lies strongly to the right, which is what we predicted initially anyway, based on our value of delta G. So at equilibrium, if you put in 1 bar of all these things, at the end, you're going to have mostly product with small amounts of these two starting materials. Cool. We're good. It works out that if you have a delta G, these are all delta G zeros. If the delta G zero for a reaction is negative 22.8 exactly, that means K is going to be large enough so that you have 99.99% products when it reaches equilibrium. For a reaction like that, for a reaction that basically reaches 99.99% product, we might not even really describe a reaction like that as being an equilibrium, even though technically all reactions are equilibria. We might just say it went to 100% products, because it went essentially to 100% products. We would probably only describe a reaction as being an equilibrium if you had, measurable amounts of products and reactants left at the end. It doesn't have to be 50-50, it could be 90-10 or something like that. But if it's 9999 to 1, we would probably call that reaction complete. We would probably call it not an equilibrium. And so this is basically just to say that that's sort of a benchmark value of delta G0. That anytime you have a delta G which is smaller than that number or a larger magnitude, negative, then we could say that that reaction essentially goes to completion. All right, so this is great. We talked about delta G0, which everything's at 1 molar. We talked about K, which is a constant, which is independent of concentrations, meaning it stays the same number regardless of what concentrations you're dealing with. What we want to do is be able to describe situations that are not under standard conditions. Delta G0 is standard. Standard concentrations, standard pressures, standard temperatures, and we can't use delta G0 outside, well, we can't, the delta G0 does not describe systems under any other set of conditions. So we needed sort of a way to extend delta G0 to these other situations which are non-standard. And this is what we're going to be doing again and again with this thermodynamics stuff going forwards, is we want to take the delta G, which is under a standard conditions, it's a reference point, it's a starting point for us, and extend that to understand systems that are under a different set of conditions. So we use K when we're talking about a system that's at equilibrium. When you have a system that's not at equilibrium, maybe it's part way, it's on its way to equilibrium, or maybe it's gone too far, it's got to go backwards to reach equilibrium. Those two sets of conditions are not described by delta G0 and they're not described by K. because K only describes systems at equilibrium. We can define something called the reaction quotient Q, which has the exact same formula as K, except it's for describing a system that's not yet at equilibrium. If it's at equilibrium, K and Q are the same thing. So Q, in a way, is like, how close are you to equilibrium? When it's equal to K, you're at equilibrium. If it's larger than K, then you went past equilibrium and you got to go backwards to reach equilibrium. Or if it's smaller than K, you have to continue in the forward direction until you reach equilibrium. So imagine this generic reaction where we have A plus B, where the small a and small b here are the stoichiometric coefficients. Is in equilibrium with C and D. So this could be something like HF plus H2O, blah, 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 right? We would define K as being, well, what we'll do is we'll define Q as being equal to these. It's concentration of products raised to their exponents divided by the concentration of reactants raised to their exponents. This is the exact same formula we already used to describe K, but K, this is only equal to K if you put concentrations of A, B, C, D in when the system's at equilibrium. So what we're saying here with Q is we can put whatever the system happens to be at, whether it's at equilibrium or not, those concentrations could go in here and we got a measure of Q. If the system happened to be at equilibrium, Q is equal to K. If it's not at equilibrium, you're going to get some other number. If you have to go to the left to reach equilibrium, that means you have too much products, then Q is going to be greater than K. Or if you have to go to the right, then you're going to have too many reactants, and that means Q is going to be less than K. Okay, so basically this is what we're saying here. At this point in a reaction, that's equilibrium, the point of minimum Gibbs energy, we would say that Q is equal to K. If you put the concentrations of all the reactants and products into that equation at that point in time, you're going to get K. If you're over here, at this point, you're not at equilibrium, but you can still define Q. You can take what your concentrations of products and reactants are, stick them into the equation that you see here, and you'll get a number for Q, which won't be equal to K because you're not at equilibrium. It'll be smaller than K, but it'll increase that number as you proceed towards equilibrium until you hit equilibrium. And if you're up here somewhere, Q is going to be greater than K. Okay, so Q is really useful because if you calculate Q for a system, you take the concentrations you're at and stick them in, you can compare them to K and tell whether you're at equilibrium, not at equilibrium, and which direction you have to move in order to reach equilibrium. So here's a problem. Here's the reaction between hydrogen gas and iodine in equilibrium with 2 moles of HI. For the reaction below, Kp equals 46 at 510 degrees Celsius. If hydrogen gas, iodine vapor, and hydrogen iodide, each with a partial pressure of 0.55 bar, are mixed in a vessel, predict what will happen. Okay, so it's saying everything here is in the same partial pressure, 0.55 bar, 0.55 bar, 0.55 bar. We know Kp equals 46. So we could say Qp is going to be equal to the pressure of Hi squared. It's squared because of the 2 in the equation, divided by the pressure of H2 multiplied by pressure of I2. So that equals 0.55 bar squared divided by 0.55 bar, 0.55 bar. This math's going to be easy, isn't it? Technically, I guess here we don't include our units, right? We don't put units when we do our Q or our K. They have to be in the right units. They have to be in bars, or if it's a QC, it has to be in molar. But we don't put them there because remember, we technically are supposed to be putting in activities, not concentrations, and activities are unitless, so you can forget about that. But basically what you end up with there is 0.55 squared over 0.55 squared equals 1. So QP equals 1, KP equals 46. So what you can see here is Q is less than K, and because Q is products over reactants, and if Q is smaller, it means you don't have enough products. So this means you're not at equilibrium. This reaction is going to have to shift to the right in order to reach equilibrium. Okay, and you can actually do one of those ICE equations here and figure out what those concentrations will be when this finally gets to equilibrium. But at this point, all we can say, though doing more calculations, is Q is smaller than K. In order for Q to increase, you need to create more products and decrease our starting material concentrations. And therefore, we're not at equilibrium. We need to shift this to the right. We need to produce more products. Wonderful. Okay. So I talked a lot today about delta G and delta G0. This is, remember I said delta G0 equals minus RT log Q, probably one of the top 10 equations you learn in chemistry ever. I'm going to put this one on that list too. What else should be on that list? Maybe the Arrhenius equation. It's a pretty important one too. Anyway, what this one is saying is the delta G for a system is equal to the standard delta G, everything at 1 bar, everything at 1 molar, plus RT log Q. So basically what this is saying is we can relate the delta G for some actual system that's not under standard conditions to the standard delta G. And the standard delta G, remember, is useful because you can get it out of a table. You can use delta G as a formation and get delta G0. So delta G0 is easy to obtain. And then we have this piece, which is a correction factor. Basically, this RT log Q is a correction factor which corrects the delta G0 for the fact that you're not under standard conditions. So basically what this allows us to do is use our delta G0 value and then fix it, modify it, make it apply to every situation. And this is very, very important, right? Because delta G0 will be kind of useless if it only ever applied to a situation where everything was 1 molar and 1 bar pressure. We don't want to use delta G0 all the time because it's too narrowly defined. It's just but it is a reference point. And from that reference point, we can get the actual important number, the delta G for a real system, by applying this equation, adding on that correction factor, RT on Q. Perfect. So this is fantastic. This basically takes everything we've learned already, the delta G0, the K, their relationship, and we can apply that now to any system we want. So here's an example. We have, it says the oxidation of SO2 gas is too slow at 298 to be useful in the manufacture of sulfuric acid. So this reaction is run at high temperature, and we know that reactions speed up when you increase the temperature. Looking at this particular reaction, is delta S positive or negative? Well, we don't know what the number is, but you can certainly guess, right? You can look at that and say, well, we got 3 moles of gas on the left, and on the right, we have only 2 moles of gas. So our delta N here is -1. This means that this is going to have a delta S that is negative. Right? Positive delta S, increase in entropy, means you're creating gas. This is absorbing gas, so it's the opposite. It's negative delta S. Doesn't matter. They're not asking us about delta S, but I just wanted to throw that out there. Calculate K at 298 and 973K using delta G0 at 298 with this number and delta G0 at 973 at minus 12.12 kilojoules per mole. Okay, so this is going to be making use of this new stuff that we're learning today. Let me just get my answer sheet up here so I don't have to do these calculations. So we wanted to find out K at 298 and 973. Okay, great. I'm gonna have to go to here. So we need delta G0, I'm gonna write this out, at 298 is equal to negative 141.6 kilojoule per mole. Delta G0 at 973 equals minus 12.12 kilojoules per mole. So K at 298, we did this a couple of slides ago. We used this same equation here, which is just a rearranged version of delta G0 equals minus RT ln Q. So K at 298, delta G at 298, no, not 928, 298 equals E to the minus 141,600 joules per mole. Again, we need the units here to match. That's negative of a negative. The temp is 298. And when you work this one out, you get a very large number, 6.6 times 10 to the 24. Okay, so this reaction at 298 strongly favors the products, right? This is 99 with, I don't know, a dozen zeros after it or more percent product when this finally reaches equilibrium. So the delta G is strongly in favor of pushing this reaction to the right and producing the SO3 gas. Although it's saying that it's too slow. Even though this has a very huge driving force for this reaction to go to product, it's too slow to be practically useful. So the rate of a reaction is just as important as whether thermodynamics will let this reaction happen or not. We also want the K now at 973. That equals E to the delta G0, 973 over RT equals E to the minus 12120 kilojoules per mole over 8.314 joules per K mole. That's joules. I converted it to joules there, multiplied by 1,000. And 973 is the temperature. And this you get 4.47. No exponents. Now, looking at this number, the rate may be way faster because you're at a higher temperature, but your equilibrium constant, I guess it still kind of favors products, right? When this reaction reaches equilibrium, I'll just show you the reaction over again here. At a high temperature, when that reaction reaches equilibrium, you do have more products than you do reactants, but it's not as overwhelming as it was at a low temperature. So sometimes you have to sacrifice, or there's this like playoff or competition between whether you want to go to high temp, which is good for rates, versus low temp, which is good for pushing towards products because of the equilibrium constant, because of the thermodynamics. Thermodynamics could be better in a low temperature, but rates are not. So you need both to work, right? You need both thermodynamics and rates to work out for you. Okay, so that's giving us our delta G0 values. Next, we're asked, two containers are filled with 0.40 bar of SO2, 0.010 bar of O2, and 0.10 bar of SO3. One is kept at 25, and the other is kept at 700. which direction, if any, will the reaction proceed to reach equilibrium at each temperature? So what we can do is find Q and compare it to the values of K that we calculated in step 1. Okay, so, well, we can do that. Look, so we have 0.4 bars. So for part B, the pressure of SO2 is equal to 0.400 bar. The pressure of O2, 0.0100 bar. And the pressure of SO3, which is the product, 0.100 bar. Our equation was 2SO2 plus O2 in equilibrium with 2SO3, everything here in gas phase. So what we can say then is that our Q is going to be the pressure of SO3 squared, because of the 2 in front, divided by the pressure of SO2 squared times the pressure of O2, which is 0.100 squared, no units, 0.400 squared, 0.0100, which is 6.25, unitless. Unitless because it's a Q, which is like K. What we can do then is compare that value to the K's up above. This is the K at 298. And what we can see is that at 298 K, Q is way smaller than K. That means reaction will proceed to the right to produce more products, to produce more SO3 gas. So we're just at the beginning here, right? We got to push this way off to the right, produce a lot more products. However, at, was it 973 K? Q is greater than K, because at those conditions, that equals K at 973. So 6.25 is greater than 973. So that means because Q is greater than K, will to the left. Okay, so under those same starting conditions, those same starting pressures that you see here and here, depending on the temperature you put them in at, it'll either proceed to the right or proceed to the left. Finally, we have the last part. Calculate delta G for the system, not delta G0, just delta G for the system in part B at each temperature. Great. We can do that easy. Delta G equals delta G0 plus RT ln Q. We know already what Q is, right? We know Q equals 6.25. So we calculated it up here. So let's start off. Let's say delta G at 298. And what this is telling us is under that particular set of pressures, these pressures that you see here, what's the driving force to move forwards or backwards? We know we're going forwards, but we don't know the delta G. We don't know what the quantitative driving force actually is, whether it's large or small. So we can calculate it. We can't use delta G0 to tell us because that assumes everything's at 1 bar, which it's not. But we can correct it using this equation. So the delta G at 298 is the delta G0 at 298 plus RT ln Q, wherever we're at. And that equals the delta G0 from 298 is given to us right in the question at -141,600 joules per mole. I converted to joules just to keep everything together. 8.314 joules per K mole, which is R. Temperature is 298 Kelvin. And then ln Q on 6.25. And when you calculate that out, you get negative 137,000 joules per mole equals negative 137 kilojoules per mole, which really isn't that different from our starting value. So the fact that we're not at 1 molar, 1 molar, 1 molar, or 1 bar, 1 bar, 1 bar, the fact that we're under non-standard conditions doesn't really change very much our actual number. It changes it from 141.6 to 137. Small correction factor, but this now applies to our actual reaction conditions, not this hypothetical ideal 1 molar everything. We can do the same thing for the delta G at 973. Remember, our delta G0 at 973, also given in the question, is 12120 joules per K mole plus 8.314 joules per K mole times the temp, 973 K, times ln 6.25, and this gives us delta G, well, delta G equals positive 2.70 kilojoules per mole. Now that's kind of interesting. We have a positive delta G, which means at that temperature, this reaction is spontaneous in the reverse direction. This reaction is going to go backwards, which is also what we predicted back in part B qualitatively, right? That's just qualitative. We know Q is bigger than K, so it's going to go to the left. Now we know exactly what the driving force is for it to push to the left. Positive 2.70 kilojoules per mole. This one, because it's negative up here, is going to push to the right to give us more products. Well, great. We are off to the races here. We kind of dealt with a lot of stuff today. Hopefully, people are feeling a little more clarity on the distinction between delta G and delta G0. We looked at some calculations, some equations that can relate them to each other. So we can convert delta G to delta G0, or delta G0 to delta G, and then the interrelationship between them and K, which is the position of a reaction. It's kind of a lot there that all feeds together, but it's all very self-consistent, right? Delta G0 and K apply to standard conditions. K is a constant, delta G0 is a constant, and that can be modified to find the delta G or the Q at any other set of conditions. Wonderful. So thank you, everybody. That is it for today. We will meet again on Friday. And even though everyone's online today, I'm happy to be here. And yeah, if any questions, as always, pop them in the chat, send me an email, and I'll do my best to help you out. Great. Don't forget the assignment due tomorrow, and then see you Friday.